Hello AP Physics students, it's Mr. Ellis, and in this video I'm going to talk to you about what happens when we have an object sitting on a ramp. Well, let's say that this object actually is moving. Let's say it has some speed v and it's being pulled. You're going to see all the same forces we've talked about before. Here we've got tension, we're going to have friction, it's kinetic in this case. The normal force is going to be actually perpendicular to the surface, and the weight straight down toward the earth. So you can see we have forces that are vectors, and we're going to have to break something up into components. What might actually make this easier is if we choose a coordinate axis that's not like your typical sideways and up and down. Like the x-axis maybe could be parallel to the surface, and the perpendicular y-axis goes like that. You'll notice the normal force is actually on that perpendicular y-axis. So the only force that's not on an axis is the weight. We have to break that one up into components, which is kind of strange because it looks like it is going straight down, but our coordinate axis is tilted, which makes this actually a lot easier. The only thing you have to do here is figure out what are those components of gravity or of the weight. You'll notice this angle here is actually the same as the angle of the entire ramp. There's like similar triangles here, interestingly enough. And the angle right here, there's this tiny triangle. So the angle of this guy is 90 minus theta, which means that since this is a right angle, which I did not draw very well, that the angle down here is actually theta, and it's the same triangle as the one over there. So this is kind of nice. That just means that the y component of the weight is going to be mg cosine theta, because that's the adjacent, and the x component is mg sine theta. So when you draw your free body diagram, it's going to actually look like this. Now on the AP exam you would only draw the blue arrows, but it's useful to draw in the component of the weight because that's going to help us set up our net force expressions. Now, in this case it's accelerating possibly in the x-axis, but it's not accelerating in the y-axis, and it usually never is. It's just going up or down the hill. So if we add up the x components, you can see there are three, right? The x-axis looks like this in this system, right? And the y-axis is like that. So we have t, if it's accelerating uphill, let's make that positive, minus the friction force minus mg sine theta. And in the y direction, we have the normal force minus mg cosine theta. You'll notice mg itself doesn't show up. That's because we've split it into its two components. Okay, so let's look at an example problem. This is kind of a more difficult situation. All right, in this example, we've only have three forces because it's just at rest. All right, that means this is static friction. So what's the friction force acting on the block? All right, how do we do this? Well, what's the net force? It's at rest. So that means the x net force is 0 and the y net force is 0, and we just need to set up those expressions. Right? Remember that the weight actually has two components. It has an x component and a y component. Mg sine theta, mg cosine theta. And you'll get used to these. It just takes a little practice. So the friction, you'll notice, is acting in the x direction, parallel to the ramp. So if we set up a net force equation in the x direction, it's going to include friction, and it's going to include the x component of the weight. Now you may also remember, friction, like static friction, has this equation, but this is for the maximum static friction, which this may or may not be. And we kind of know everything else, right? Like we know this is 0, and we know mg, we know sine theta, so that's all we need. That maximum force, if we wanted to know it, we could solve for the normal force, which I can show you how to do in a second. But in this case, this is all we need, right? We've got one unknown, so do the math, and it's that. If we really wanted to know the normal force, all we would have to do is look at the y, right? Because in the y direction, we have n minus mg cosine theta, and you just follow the same steps. All right, thanks for watching, guys. Good luck on these problems.